The moment of inertia can be calculated by the formula mr square divided by 2. There are two important theorems in explaining moment of inertia. One is the parallel axis theorem and the other one is perpendicular axis theorem. The moment of inertia of a disk about any of its diameter is mr square divided by 4. Hello everyone. Welcome to session 3 of chapter 7, System of Particles and Rotational Motion. This is Swati, Department of Physics, Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. So, dear children, in the previous session we had a discussion about the moments of inertia, and when we derived about some important derivations, and we have derived a relation between the terms which are related with rotational motion. So, in today's session, let us begin with the study of the moment of inertia of some regular shaped bodies by analyzing the table. So, here we have few important definite regular shaped bodies and their moment of inertia are mentioned. So, in this table, we are going to have a discussion about their axis of rotation and the formula to find the moment of inertia and a typical diagram or a reference diagram to understand the axis of rotation of a given body. So, let us begin with the first one, that is the thin rod of length L and mass M. Say for example, our body is a thin rod which is having definite length of L and its mass, say for example M. Then their axis of rotation is perpendicular to the rod at the midpoint. You can observe the axis of rotation for a thin rod is midpoint and it is perpendicular. So, this is how it rotates. The formula to find the moment of inertia is ml square divided by 12. What is m here? The mass of the rod. L is the length. Similarly, the next one we have thin circular ring of radius r and mass m. Say for example, I have considered a circular ring of radius r. It is having some mass m. Their axis of rotation. The axis of rotation of a circular ring will pass through the center and it is perpendicular to its plane. Say for example, we have a thin ring, circular ring. So, the axis of rotation is perpendicular to the plane and it passed through the center of the ring. And next one, thin circular ring of radius r and mass m. Say for example, if you have taken ring, a thin circular ring in this manner, then the axis of rotation is it passed through the diameter. The axis of rotation passed through the diameter and it rotates like this. The formula to find the moment of inertia for circular ring is mr square by 2 when the axis of rotation is passing through the diameter. If for the same ring, if the axis of rotation is through the center and perpendicular to its plane, then the formula to find moment of inertia is mr square. Similarly, we have circular disk of radius r and mass m. Now we are talking about disk. So, in the previous example, we have considered a circular ring and now we are considering a circular disk and its axis of rotation is perpendicular to the disk and it lies at the center. Say for example, you can refer this, we have a circular disk, the axis of rotation lies at the center and it is perpendicular to the plane and the formula is mr square divided by 2. Similarly, we have circular disk of radius r and mass m. If the axis of rotation is passing through the diameter, then the formula is mr square by 4. What is the difference between this condition and the previous one? Here the axis of rotation is perpendicular to the disk and at the center. If I have a disk, if the axis of rotation is perpendicular to the disk and at the center, then the formula is mr square by 2, and if it is passing through the diameter, then the formula is mr square by 4 is what the difference. And now we are considering a hollow cylinder of radius r and mass m, and the axis of rotation is nothing but the axis of cylinder, then the formula is given by mr square. You can observe the axis of rotation is the axis of cylinder, then the formula is mr square. This in case of a hollow cylinder. If you consider a solid cylinder which is of radius r and mass m, then is the axis of the cylinder, and the formula is mr square divided by 2. The moment of inertia can be calculated by the formula mr square divided by 2. Here the difference between these two is, one is the hollow cylinder, the other one is the solid cylinder. And next we have sphere of radius r and mass m. If you consider an object that is a sphere whose radius is r and it is having a mass m, then the axis of rotation passing through the diameter. And the formula to find the moment of inertia is 2 by 5 mr square. So this is how you can remember by visualizing the object and the axis of rotation by the diagrams. It is so simple for you to write the formula in the relevant cases. So we have already studied what are the terms that involved in rotational motion, and one of which is moment of inertia. There are two important theorems in explaining moment of inertia. One is the parallel axis theorem and the other one is perpendicular axis theorem. This is very important examination point of view. Let us study now what is parallel axis theorem. What is the statement? So it states that the moment of inertia of a body about any axis, the moment of inertia of body about any axis is equal to moment of inertia about a parallel axis which is passing through its center of mass plus the product of its mass and the square of the perpendicular distance between the two axes. So you can remember this statement in a simple way by just understanding the diagram. So we have considered a rigid body here whose mass is given by m. And let us say AB is a parallel axis which is passing through the center of mass, and we have a CD which is parallel to this axis AB. So the distance between these two, say for example R. So now according to parallel axis theorem, the moment of inertia of a body, the moment of inertia of a rigid body about any axis is equal to, that is I is equal to the moment of inertia about a parallel axis passing through the center of mass. Moment of inertia of a parallel axis passing through the center of mass, that is, I can write it as ICM, that is inertia which is passing through its center of mass plus the product of mass and the square of the perpendicular distance between them. So the product of mass and the square of the perpendicular distance between the two axes. Here the perpendicular distance between two axes is r. So the square of the perpendicular distance, that is mr square. Just by understanding or remembering this expression, you can easily write the statement. To explain this question or to write the answer for this question, that is to state and explain parallel axis theorem might be the question, then you have to write the statement with diagram, then expression. After that you have to explain the terms which involved in this. So let us derive it now. So in this figure, as I told, m is the mass of the rigid body, AB is the axis which is passing through the center of mass, and CD is another axis which is parallel to AB. You can observe CD is another axis which is parallel to AB. Now RB, the perpendicular distance between two axes. So this is the perpendicular distance R between two axes. So from parallel axis theorem, moment of inertia I of the body about the axis CD. So from this we can write the moment of inertia of I about the axis CD is equal to the inertia about the center of mass plus the mass of the body and the square of the perpendicular distance between two axes. So this is how we can find the inertia. By knowing the inertia of one axis, we can also find the inertia of a body which is passing through the parallel axis. As I mentioned before, it is so important to write the statement properly and to explain this theorem with diagrams. So to understand statement or to write the statement, first we must know about what is perpendicular axis theorem. So remembering the lengthy statement is difficult for few students. So you can do some strategies in remembering this. For that, let us first understand diagram and let us first remember the expression. Then you can easily write the statement. But so let us go through the statement now first. The moment of inertia of a plane lamina. The moment of inertia of a plane lamina about any axis perpendicular to its plane is equal to sum of moments of inertia of plane lamina about any two mutually perpendicular axes in its plane, so that all three axes have the same point of intersection. Say for example, this is a plane lamina I have considered. A plane surface I have considered, where we have x-axis, y-axis as well as z-axis, and the moment of inertia along z-axis is Iz. So it is saying that the moment of inertia of a plane lamina about an axis perpendicular to its plane is equal to, here we have an axis which are perpendicular to each other and it is also perpendicular to the plane. So any one axis along which we can find the moment of inertia which is perpendicular to the plane is equal to sum of moments of inertia of a plane lamina about any two mutually perpendicular axes in its plane. So the condition is all three axes must have the common point of intersection. So this entire statement on a whole is explaining that we can find the moment of inertia of any axis which is perpendicular to lamina. Say for example, in this example I can write Iy, which will be equal to the sum of moments of inertia of plane lamina about any two mutually perpendicular axes. Here Ix and Iy also mutually perpendicular to each other. The sum of moments of inertia of plane lamina about any two mutually perpendicular axes. So let us explain this now. So in the figure, as I told you, so the plane lamina is in xy plane. So the plane lamina we considered in xy plane. Now I have to write the moment of inertia for z plane. The plane lamina lies in xy plane. I have to find the moment of inertia along z plane. So how to write the expression along z? That is what we have to understand. So z axis is perpendicular to the plane of plane lamina. So if this is a plane lamina, even z is the perpendicular axis to the plane. So O is the common point of intersection of three axes. And I told you Iz is the moment of inertia along z-axis and Ix is the moment of inertia along x-axis. Iy is the moment of inertia about y-axis. Then according to perpendicular axis theorem, the moment of inertia along z, that is Iz, can be calculated by taking the sum of moments of inertia of two mutually perpendicular axes, that is Ix plus Iy. So simple, Iz is equal to Ix plus Iy. Similarly, we can also write the expression for moment of inertia of any axis which is perpendicular to the plane. So this is all about perpendicular axis theorem. Now let us analyze what are the applications of the moment of inertia. So now by using the theorems of moment of inertia, let us derive an expression for moment of inertia of a disk about its diameter by using perpendicular axis theorem. So far we have studied about the theorems of moment of inertia, that is parallel axis theorem and perpendicular axis theorem. Just now we had a discussion about perpendicular axis theorem. By using perpendicular axis theorem, we need to derive an expression for moment of inertia of a disk, which is about its diameter. So consider this disk. So this is a disk whose axis of rotation is along the diameter, and we have x-axis. The inertia along x-axis is given by Ix, moment of inertia along y-axis is Iy, and this y is perpendicular to the center and it lies at the center of the disk. So Iy is equal to ICM, that is inertia of center of mass, and along z axis the moment of inertia is denoted by Iz. So they all meet at a common point at O. So O is the common point of intersection of all the three axes. So consider a disk of mass m and which is having a radius r. So x and z axis lies in the plane. We are saying in the plane x and z axis lies, but y is perpendicular to the plane or perpendicular to the disk. O is the common point of intersection of three axes, and I told you Ix, Iy and Iz are the moments of inertia about x, y and z axis respectively. Now according to perpendicular axis theorem, we know that Ix and Iz are lying in the plane. If this is the disk, Ix and Iz are lying in the plane along x and z axis respectively. Iy is perpendicular because y-axis is perpendicular to the disk. So now we have to find the moment of inertia along y-axis. So from perpendicular axis theorem we can write inertia about any axis which is perpendicular to the plane is equal to sum of moments of inertia of other two mutually perpendicular axes. So sum of moment of inertia, that is Ix plus Iz, which are mutually perpendicular. So Iy is equal to Ix plus Iz. So we know that x and z are equal, that is the moment of inertia along z is equal to moment of inertia along x axis. So Iz is equal to Ix, and hence the above expression becomes Iy is equal to Ix. This Iz also I can write it as Ix only. So Ix plus Ix becomes 2Ix. So the moment of inertia of a disc whose axis of rotation is about its diameter is given by mr square divided by 2, which is equal to 2Ix. Now this gets multiplied here and we get mr square is equal to 4Ix, or we can write it as Ix is equal to mr square divided by 4. That is because we know the center of mass, moment of inertia of y, that is moment of inertia of center of mass is mr square divided by 2. So we will get Ix is equal to mr square divided by 4. So the moment of inertia of a disc about any of its diameter is mr square divided by 4. So now let us consider another object, say for example thin rod, and let us derive an expression for moment of inertia of a thin rod. This is also one of the application of the theorems. So here I have considered a thin rod of length L. This is my rod whose length is given by L, and AB be any axis which is passing through the center of mass of the rod. So CD is the axis which is parallel to the distance. So CD is the another axis which is parallel to line AB, and the distance between them, let us say it as L by 2. So let I be the moment of inertia of axis CD. So from parallel axis theorem, we know that the moment of inertia I is equal to ICM plus mr square. We have derived this expression from parallel axis theorem. So we can substitute now the relevant terms in our example. So here r is nothing but the distance between two parallel axes. So I as it is I am retaining, which is equal to ICM plus m into, here r is nothing but the distance between two axes, that is L by 2. So we are writing L by 2 the whole square, because from the parallel axis theorem, our axis theorem says that ICM plus mr square, and hence it is L by 2 the whole square. So we can write it as I is equal to, what is this center of mass or inertia of center of mass for a thin rod? It is from the chart we can analyze again. You can go back to the chart and have this value. It is given by ml square divided by 12 plus ml divided by 2 the whole square, or we can write it as ml square by 12 plus m into L square divided by 4. So from this I can take ml square divided by 4 common, and taking ml square by 4 outside, I remain with 1 by 3 plus 1. So here taking the LCM again, ml square divided by 4, here in the denominator 3, 1 plus 3. So I will get ml square divided by 4 into 4 divided by 3. So this 4 and 4 can get cancelled, and I value will be equal to ml square divided by 3. That is the inertia, moment of inertia about an axis CD, which is given by ml square divided by 3. Similarly, let us derive an expression for the kinetic energy of a rolling body. Say for example, if you have a circular object, a body, if the body is rolling over a surface, it will be having both translational motion as well as rotational motion. We have to derive an expression for kinetic energy of a rolling body. So for that, let us consider a body of mass m which is rolling over a surface without slipping as shown in the figure. So it is rolling over this surface, and this body is having a mass m, and the kinetic energy of the rolling body is equal to the sum of translational energy because it will be moving forward and it will be rolling and rolling. So it is sum of translational kinetic energy plus rotational kinetic energy. So the translational kinetic energy, what is the expression for kinetic energy? It is half mv square. So we are talking about the kinetic energy of a body whose velocity is nothing but the velocity of its center of mass. So you can write it as half mv suffix cm, which says that the center of mass square plus for a rolling body the kinetic energy or a rotational kinetic energy is given by half I omega square. So it is I omega square divided by 2. So sum of translational kinetic energy plus rotational kinetic energy. So now VCM is nothing but the velocity of center of mass of the body and omega is the angular velocity. If the body is rolling and rolling, it will be having the angular velocity and it is denoted by omega, and I is the moment of inertia of a body. But what is this velocity of center of mass? We know that the relation between linear velocity and angular velocity, that is V is equal to R omega. So VCM is equal to omega R, and from this we can write omega is equal to VCM divided by R. What is R then? It is nothing but the radius. So radius of the given body. So moment of inertia I is equal to mr square, where R is the radius of gyration. We know moment of inertia definition, that is nothing but I is equal to mr square, R is the nothing but the radius of gyration. So from this we can substitute in equation 1. So what do we get? Kinetic energy is equal to mv square divided by 2. Here V is nothing but the velocity of center of mass and hence it is mvcm the square divided by 2 plus here we have the kinetic energy of rotational motion, that is given by mr square vcm the whole square divided by 2r square. Because our expression for I omega square by 2 for rotational kinetic energy. So what is I? I is mr square and omega is nothing but V divided by R. From this we get to know V divided by R. So V omega square we have. So VCM the square divided by R square into 2 already we have in the previous expression. So now from this, by taking mv square cm by 2 common, what do we remain? This entire term will come out and we'll get 1 here and plus. So we remain with, here I have taken only m and v term outside and r term is as it is I am writing, and here 2 has come out and we remain with r square in the denominator. So I'll get 1 plus r square, that's capital R the whole square divided by r square in the denominator. So this equation applies to any rolling body such as a disc, a sphere, a ring or a cylinder. So to find the kinetic energy of any body which is rolling, we can calculate the kinetic energy. We can make use of this formula, whether it may be a ring or disc or any cylinder or any sphere. So these are the applications of the theorems what we have studied based on moment of inertia. So in this session we have learnt about perpendicular axis theorem and the moment of inertia of various definite shaped or regular shaped objects, as well as the applications of the theorems what we have studied, that is the parallel and perpendicular axis theorem. We even derived an expression for kinetic energy of a rolling body. So in the upcoming sessions, let us learn some other interesting concepts. Until then, keep learning all of you. Take care. Thank you.